All right, hi everybody. Back again with chapter 9 today. So this is Chemistry 4. This is Chem 4, Week 9, and this is video number 1. So we're going to start by making a little schematic here, a little flow chart on in order to get to solutions. So let's start at the very top with mixtures. And the definition of a mixture is a physical combination of two or more substances. Now off to the left here we have something called heterogeneous mixtures, and on the right hand side we have homogeneous mixtures. So let's take care of the left hand column first. It's not as important in this chapter. So heterogeneous mixtures are not uniform throughout. They're not consistent throughout. They have different types of consistency all throughout the entire sampling. So they have regions of varying composition, and some examples off the top of my head here when writing these notes were a rock, mud, salad dressing, and the particles are very large and they're easily separated away from each other by physical means, something like filtration or even using like forceps and just moving different samples away from each other. So heterogeneous mixtures are not really the focus of this chapter. The right hand side is. So mixtures that are homogeneous mixtures are uniform and consistent throughout. They have the same composition no matter what part of the sample you take from. And on the right hand side here I've written colloids. Your book also talks about something called emulsions, but colloids, emulsions, these contain larger particles than in solutions. So solutions is the middle column here, working our way down this page 1 of our notes. I put 2 stars on solutions because this is our main focus. So solutions, they contain particles the size of an ion or a molecule or even atoms. All right, so homogeneous mixtures, they're uniform and consistent throughout. They have the same composition all throughout the sample. And one example of this is a solution. And examples of solutions are salt water, air, wine, and brass even. Brass is a solid solution. Solid solutions are called alloys. Now, in colloids and solutions, both of these guys, dissolved particles are too small to be separated out by something like filtration in a lab. Instead, we have other techniques to do that. All right, so page 2 of today's notes. And again, this is chapter 9 from your book. We're on video number 1 for week 9. Question: what determines if a substance is soluble in a given liquid? So some substances are soluble in a given liquid, like water, and some substances are not soluble in a given liquid. So the answer to this question is a substance's solubility, whether or not a substance is soluble in something, a substance's solubility can be predicted by the phrase like dissolves like. So essentially, polar substances are going to dissolve in a polar solvent, and nonpolar substances are going to dissolve in nonpolar solvents. All right, so let's say that again. What determines if a substance is soluble in a given liquid? Well, a substance's solubility can be predicted by the phrase like dissolves like, which means that substances with similar intermolecular forces form solutions. Now, what do I mean by similar intermolecular forces? I just mean that for the extent of this video, let's just say that if a molecule is polar, it's more than likely that that polar molecule is going to interact favorably with other polar molecules. So, number 1 here says polar solvents. Now, the solvent is the substance that does the dissolving. Almost always in a general chemistry class such as ours, or a general organic and biochem class such as ours, that solvent is usually water. So polar solvents, examples are H2O, water, ethyl alcohol, CH3CH2OH, and they dissolve polar and ionic solutes. Solute is what gets dissolved. So nonpolar solvents, for example, hexane, C6H14, oils, fats, these are only going to dissolve nonpolar solutes. Like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. All right, so page 3 of today's notes, let's talk about the dissolving process. How exactly does something like water, for example, dissolve a salt like NaCl? How does it do that? And what it does is the water breaks up the NaCl and gets around the individual Na plus ions and Cl minus ions. This process in general is called solvation, but when water is doing it, it's called solvation. So as an example, NaCl, solid. That's my solute. That's what gets dissolved. And then water is my solvent. Solvents are what do the dissolving. So here's what's going to happen, and I'm going to draw you a picture. The solvent, water, approaches the solute, NaCl, and slowly solvates the individual ions, in this case ions, but it can also do this with molecules. So I've drawn an Na plus ion, and we would want the delta negative parts of water to interact. Remember when we talked about Lewis structures and polarity? So the Na plus is hydrated by what I've drawn. There are 4 water molecules. Likewise, the Cl minus ions are all going to be hydrated by the hydrogen ends of the water molecules. So I've got the positive ends of water interacting with Cl minus. I've got the negative ends of water interacting with the Na plus. Now, when water does this process, it's called hydration. In general, though, with any type of solvent, it's called solvation. All right, let's do an example. Which of the following are solutions? Remember, solutions are homogeneous mixtures. They're consistent throughout. Italian salad dressing, rubbing alcohol, and algae in pond water, and black coffee. All right. Italian salad dressing is not a solution. It's not uniform throughout. Rubbing alcohol is a solution because it's the same. It's got consistency throughout. Black coffee, consistent throughout. So black coffee and the rubbing alcohol were solutions. Another example. Which of the following pairs of substances would form solutions? In other words, which following pairs of substances have similar characteristics? For example, polar and polar versus nonpolar, polar, etc. So we have to kind of rely on some Lewis structures and some of the stuff we've done in the past. In C, you see that they look exactly the same, and in D, you see that they look exactly the same. So for A, CCl4 plus water, these are not going to form a solution because CCl4 is nonpolar, water is polar. Gasoline plus MgSO4, gasoline is a nonpolar solvent, and magnesium sulfate is an ionic compound, which is as polar as it can get. For C and D, the structures look so similar that you can assume, in this case, that they would probably be able to form solutions with each other. So that's how you want to do this. So for C, you got C6H14, C7H16. Yes, they are going to form a solution. The last one is C2H5OH, C7H15OH. They look the same. Chances are they're going to be able to form a solution. All right, let's take care of some vocabulary at the bottom of this page of our notes here. Some solubility terms. I have 2 terms I want to introduce to you. Your book doesn't necessarily introduce these terms, but they are important. Miscible. Miscible is when 2 liquids are mutually soluble in each other. For example, alcohol and water. Right? You can freely mix alcohol and water. These 2 substances are said to be miscible. Immiscible is when 2 liquids are not soluble in each other. So if I put these 2 liquids in a test tube and shook them up like this, I would get 2 layers in the test tube. Something I can think of are oil and water, right? These are immiscible. They're going to form 2 layers. They're not going to want to interact with each other. So miscible, soluble, immiscible when 2 liquids are not soluble in each other. And I'm talking about liquids here. It's a liquid versus another liquid. Okay? So just a note, some liquids are only miscible up to a certain point, and after that, no more solute can dissolve. So that would be a temperature dependence. So whether or not two liquids are miscible or not depends on temperature. All right, let's move to the top of our next page of notes here. And it says the solution is said to be saturated. Now, what does that mean? A saturated solution is a solution in which the solvent can no longer dissolve any more solute. We've already dissolved as much solute as we're going to be able to dissolve in that amount of solvent at that particular temperature and underneath those and under these particular conditions. So definition of saturated. It's the maximum amount of a substance that will dissolve in a given amount of solvent at a given temperature, and that's called the substance's solubility. So it says there in grams per 100 grams. What that means is that's how many grams of solute I can dissolve per 100 grams of solvent, and that's usually water. Now let's take a look at the following solubility chart. I've grabbed this from your textbook, and I'm going to put a print of it down here on the bottom right. But looking at the following solubility chart for various compounds, various salts, estimate the solubility of NaNO3 in water at 40 degrees Celsius. So NaNO3 is our solute, and we're dissolving it in 100 grams of water according to the chart. So at 40 degrees, if you just go, do rise over run, first you have to find the curve for NaNO3, right? And then at 40 degrees, you just kind of do rise over run. The solubility of NaNO3 at 40 degrees Celsius is 100 grams for every 100 grams of water you have as solvent. Okay. Now remember, the density of water is essentially 1, so it's the same thing as 100 grams per 100 milliliters of water. Now at 60 degrees, we've cranked the temperature up, right? So if we turn the temperature up, we would expect to be able to dissolve more solute, and in fact we can. So at 60 degrees, we can't dissolve just 100, we can dissolve 120 grams in the same amount of solvent, right? So generally speaking, I'm writing it down over here on the right. Generally speaking, as the temperature goes up, the solubility of a substance generally also goes up. Okay, that's not always true, but by and large, it's true. All right. So in the next video, it'll be video number 2. We have 3 videos this week on Chapter 9. The next video that I'm going to talk about continues our discussion with things like molarity and solubility. And you want to watch that one right now. The third video is 2 new topics. It's got mass percent in it, and it's also got dilutions in that one. And then we're going to do, at the end of video number 3, I have a bunch of sample homework problems I've done for you. All right, so watch video number 2 now. All right.